Hello and welcome to the 2024 SEA Symposium. On behalf of the Texas Atmospheric and Space Research Team, I want to extend our most heartfelt appreciation for your attendance while we present our research and experimentation. Let's begin.
Hi, I'm Isha Bhatia and I'm from New Jersey.
My name is Imelda and I'm from Seattle.
Hi, I'm Annika Lindhorst from Seattle, Washington.
Hi, I'm Aika and I'm from Montana.
Hello, my name is Felder and I am from Idaho.
Hi, I'm Rania Marrero-Alattar and I'm from Puerto Rico.
Hi, I'm Sadie Lemmer and I'm from Miami, Florida.
Hi, my name is Rhea, Wadhwa and I am from Houston, Texas.
Hi, my name is Qian and I'm from Houston, Texas.
Hi, my name is Walti and I'm from San Francisco, California. We also had wonderful mentors, including Melissa Pore, Bob Twiggs, and Nick Pugh, who helped us along every step of the way. Melissa is a passionate educator with over 25 years of teaching experience and has led 3 student satellite missions to space. Professor Twiggs co-developed the CubeSat and contributed to educational designs like the CricketSat and Pocket Cube. Nick collaborates with Professor Twiggs on SlimSat development, and he partners with the University of Louisiana.
Our research topic focused on establishing meteorological relationships by using data collected from remote sensing and discovering new ways to utilize remote sensing.
Our group was interested in analyzing environmental and changing atmospheric conditions. Our team collected meteorological data remotely via a SlimSat payload. The payload is equipped to gather comprehensive data including altitude, humidity, temperature, pressure, voltage, and GPS data. The data we collected enables us to predict patterns and understand the effects of environmental factors. SlimSats are data collectors that enable vast research and exploration opportunities. Remote sensing paves the way for new space applications, grants accessibility of space research to the public, and is an affordable and efficient method of collecting data across the globe.
Altitude ballooning is important because it allows for the collection of atmospheric data at various altitudes using balloons equipped with scientific instruments. These balloons can reach heights of up to 40 kilometers, providing a unique vantage point for studying the atmosphere. This method is more cost-effective and flexible compared to other approaches, making it ideal for targeted high-resolution atmospheric studies. The data collected can significantly improve the weather prediction models and enhance our understanding of climate change, leading to better informed decisions and policies.
And now for our logistics.
Before we launched our main mission and balloon, we did a variety of skill preparation. Before arriving in person to Austin, we had several virtual team meetings where we discussed logistics about the project and were given presentations about space concepts like orbits, satellites, and telescopes. Once arriving, we practiced soldering techniques with a jiggy board, which is a mini practice circuit board made by Bob Twiggs, our mentor, which allowed us to gain familiarity with manipulating components in circuit boards like resistors, batteries, motors, etc., and understanding how they work in conjunction.
We practiced data collection with TinkerSats. This allowed us to gain a better understanding of how sensors are implemented into circuit boards along with the other components to collect the data and easily analyze it on a computer. Electronic components on this payload include the Chow microprocessor, the BME-280 which measures humidity, and the 3-axis accelerometer which allows us to measure the direction of movement. This was an important stepping stone towards our understanding and use of the SlimSat.
The main component of our payload was a SlimSat, which is currently in development by our mentors as a cheaper and more accessible version of Bob's previous design, the CubeSat. On the slide is the hardware block diagram for the SlimSat showing how each component is connected on a circuit board. The main components consist of the UHF radio, which is the communication hub that allows us to connect with the satellite, a JAO, which acts like the brain of the satellite, and SGP-30, BMP-180, BME-680, which allows us to collect data on tons of atmospheric variables.
On the software side of things, our team utilized Adafruit. Adafruit is a platform that projects sensor data, presents maps of both the balloon and the chase team, and displays the graphs of the data given by the weather balloon. These 3 aspects were critical to our team in terms of communication and data analysis. The graphs transmitted from Adafruit allowed us to draw relationships that support our research topic in conjunction with maps presented on the platform, which allowed me to communicate with the chase team regarding the location of the balloon and its proximity to the SlimSat payload.
After learning about various concepts and the capabilities of our software and hardware technology, we developed a set procedure for the different stages of our high altitude balloon launches. Here is a brief overview of our procedure. During the pre launch, we focused on setting up communication networks and technology, prepared the balloon, and attached the payload. During the launch, we were constantly tracking our balloon and monitoring the live feed data. And after our launch, we reflected on our procedure and compiled the data we collected.
For the setup, we used a weather balloon, SlimSat, payload housing, helium, fishing wire, a scientific scale, scissors, and a Sharpie. For the launch, we used communication devices, laptops, and Zoom. For operation, we used Adafruit, a Yagi antenna, path prediction, and Zoom. And for the chase, we used a net, notebooks, Zoom, antenna, and hats or sunglasses.
Now we will detail the varying team roles essential for the successful execution of this project.
My role as team lead consisted of many responsibilities, but the most emphasized portion of my role was communication. During the launch, I had to communicate with all of the sub-teams of my group to ensure that everything went as planned and that we were all in the loop. To simulate radio talk, our team used Zoom and said over when we were finished speaking. Although the rule of saying over was a bit redundant and silly, it ensured that all of our comments were acknowledged, which contributed to a successful launch and payload retrieval.
So for weather surveillance during each of our launch days, whether tethered or untethered, I was in charge of continuously checking and updating the team on changes in wind, gusts, and wind direction based on information from the Weather Channel. This information enabled the team manager and the team to determine if we were able to continue to follow our procedures and launch the balloon.
The balloon management team played a crucial role in preparing the balloon for launch. Imelda and I filled the balloon with the necessary amount of helium to achieve the desired lift for the mission. Additionally, Annika and Caidon securely attached the payload, which included a camera module, TinkerSat, and Arduino, ensuring everything was properly secured for a successful launch. During our tethered launch, we managed the balloon, making sure that it didn't get stuck or fall to the ground. During the untethered launch, our team was also responsible for launching the balloon.
We received signal from the balloon using a 70-centimeter Yagi antenna that we set up in different locations, including the parking lot and the Center for Space Research roof, to collect data. To track the payload with the antenna, we used information on altitude and direction of the balloon given by the tracking team to make directional adjustments. We did this until we lost the signal, which was announced to the team.
Tracking team, we create predicted flight paths based on known information like coordinates, launch time, burst altitude, and information we're assuming like ascent rate and descent rate, using a platform called StratoFlight, which considers the wind patterns for that specific day and time.
However, this pre-launch predicted path isn't completely accurate since we are assuming ascent and descent rate. Thus, when the balloon launched, we manually calculated the ascent rate along with updating the location and altitude to generate more accurate predictions. Simultaneously, we tracked the balloon using both AirTags and an Adafruit GPS. Our tracking was then communicated with both the chase team, who tried to arrive to the predicted landing site, and the receiving team, who needed the location to adjust the antenna and point it to the balloon.
Tracking team, we create predicted flight paths based on known information like coordinates, launch time, burst altitude, and information we're assuming like ascent rate and descent rate, using a platform called StratoFlight, which considers the wind patterns for that specific day and time.
As the chase team, our main mission was to track and retrieve our payload by receiving information from ground tracking and redirecting where to drive as our flight path changed. Throughout our different steps, we utilized the Yagi antenna with the help of Chris in order to receive information and data from our payload and determine general location.
We documented cloud cover and weather conditions, serving as indicators of altitude and potential variations throughout the flight. This information was vital for accurate data interpretation post-trial. Using my phone, I recorded the entire retrieval process, capturing valuable footage and observations for later analysis. We safely retrieved the payload and were able to gather data crucial to our research topic. We were able to share our project with Miss Karen Quinlan, a local resident whose backyard we found our payload in.
Now, let's delve into the critical insights and outcomes from each of our high-altitude balloon trials.
For our first flight, which was tethered, our main goal was to get hands-on experience in the roles we had chosen prior to our untethered launch day. As you can see from the slide, the weather was quite optimal with high levels of visibility and no extreme wind conditions. For this trial, we attached 2 TinkerSats and a camera module as the balloon's payload. The mass of our payload ended up equaling 190 grams, and so we had to fill up our balloon with a ton of helium until it reached a lift of 225 grams. So in reflection, our first trial showed us how easily it is to feel overwhelmed when you are not sufficiently prepared, and the importance of really feeling solid in your position in the team. Overall, our main takeaways consisted of remeasuring the 30-foot increments for accuracy so we know exactly how far away the balloon is, taking accountability for decisions and helping others when you feel it is needed, while also ensuring you are doing your assigned role for the team first and foremost, and making sure to record and document everything, since it is beyond important for looking back on what could have gone better in the process and to be used for this very presentation.
Our second trial was a tethered flight and payload cutdown that we conducted on July 12th. The main goals of this trial were to practice cutdown procedures and collect data mid-air using a SlimSat. The trial took place from 2 to 3:15 p.m. in challenging conditions. It was 91 degrees, cloudy, stormy, and humid, with winds from the south to southeast at 9 miles per hour and gusts up to 15 miles per hour. For this trial, we attached a 165-gram SlimSat payload to balloons, which provided a total lift of 280 grams. After our second trial, we were able to collect and analyze our data. We compared the relationship between altitude and temperature, noticing that as altitude increases, temperature decreases. We also examined the relationship between humidity and altitude, noticing that humidity increased as altitude increased. This was a very successful test, since we were able to use remote sensing to confirm these known relationships.
Reflecting on the process, it was crucial to have a room with Wi-Fi for the manager and to use Zoom for communication between groups. Each team member was also advised to use earbuds or wireless headphones to stay connected via Zoom. Following Rhea's instructions were essential, especially for launch timing and the cut-down procedure.
Our third and final trial was an untethered flight that we conducted on July 16th. The main goals of this trial were to track the balloon using Strataflight, Adafruit, an Apple AirTag, and the Yagi antenna. We also wanted to collect relevant data to support our research topic, carry out a cut-down procedure, and efficiently locate the payload. The payload remained in the air from 3:06 p.m. to 3:20 p.m. We were fortunate to have ideal conditions as the temperature was 93 degrees, the humidity was roughly 51%. There were 10-mile-an-hour winds from the south with 17-mile-an-hour gusts, and the skies were fairly clear with some minor cumulus clouds around the launch site. For this trial, we attached a 220-gram SlimSat payload on 2 balloons, which provided a total lift of 260 grams.
Through the data that we collected on the high-altitude weather balloon, we were able to measure temperature, humidity, and air pressure and see their relationships with volatile data. Furthermore, from this research, we were able to see the necessity and benefit of having different modes of data collection through our high-altitude balloon. Although it is possible to simply look up these relationships, our high-altitude balloon allowed us to understand the dynamics of the sky from a different perspective, one beyond what we could see with the naked eye. From the data, we saw that both humidity and temperature and air pressure and altitude had inverse relationships, meaning that as one went up, the other one went down. We predicted that our balloon reached heights upwards of 5,000 feet, but our payload was cut down before the sensor was able to capture this. The max altitude, as read on the sensor, was approximately 490 meters, equivalent to 1,600 feet. At the highest altitude, we also noticed the lowest air pressure at 101,133 pascals. Similarly, when we reached our highest temperature of 109 degrees Fahrenheit, we also recorded our lowest humidity level at 17.1%. These results are reflected in the graphs.
Launch, the team generated a predicted flight path as shown in the image on the left, with a predicted landing site to be 2.4 kilometers away. This path was generated with the assumption of the balloon having a 5 meter per second ascent rate and a 10 meter per second descent rate, but we did the calculation with a 500 meter launch altitude, which was inaccurate and significantly affected the accuracy of our prediction. Then, as the balloon launched, we began to calculate the actual ascent rate. However, as previously mentioned, the altitude sensor readings became constant, thus we approximated the ascent rate to be 1 meter per second, creating the path shown on the right. However, this path was also not applicable since the reason we were receiving constant altitude readings was that the payload string attaching it to the balloon got cut early, meaning our package fell to the ground. Our first takeaway from this is that during the flight, the GPS on the Adafruit was not working, so we had to rely mostly on the AirTag GPS, but both of these GPS took a while to update. The actual flight path, the Adafruit and AirTag GPS started working towards the end, and the location became constant, where the balloon appeared to have landed in Miss Karen Kinland's backyard, 0.6 miles away, as shown in these three figures. The chase team utilized data of the strength of the signal between the payload tracker and the Yagi antenna to find the payload on the ground. Our second takeaway is that the flight path was compromised since our weighing of the balloon and payload mass was inaccurate and it affected the lift and thus flight path. Our third takeaway is that our predicted flight path was also compromised due to the friction within the payload that caused the string to cut early and the payload to fall to the ground.
In addition to the official 3 trials, we conducted a 4th tethered trial with only a camera as our payload, with the sole purpose of exploring the physical limits of our data collection range. Instead of focusing on collecting sensor data, we focused more on the mechanics of balloon launching, considering wind speed, direction, and launch area to determine a new strategy of balloon launching that was more efficient. We were able to release the balloon 559.5 feet into the air and collected these screenshotted photos.
Our project emphasized continuous improvement through analysis of each trial. The following are our key learnings and insights.
There were times throughout the project where we were not on the same page and where it felt difficult to communicate truthfully with one another about our concerns with the project. We also faced disagreements and misunderstandings that likely contributed to us postponing further progress on our project. Whether it was learning how to desolder on the jiggy board or figuring out how to fill the balloons, we encountered many situations where we learned from trial and error and employed the engineering processes of problem solving to finally make breakthroughs.
That being said, we learned so much throughout this internship regarding the value of teamwork, precise procedure, and learning from failure that allowed us to consistently bounce back from our missteps. For us, it helped a lot to break down everything into smaller roles and steps and allow people to do what interested them the most. We also managed to successfully find and retrieve our payload despite our GPS malfunctioning because we were extra prepared and used 2 tracking devices instead of 1.
We want to give a special thanks to our wonderful mentors, who not only provided us with their skills and knowledge throughout this internship, but also allowed us to explore and have fun. From talking about black holes, the formation of atoms, and questions like, how do the sensors know what to collect? Bob, Melissa, Nick, and Chris answered our questions with full spirit and motivated our interests throughout this internship.
Throughout this project, we learned valuable key skills and lessons that we will be able to implement into our future careers. By working in a large team, we greatly improved on evenly delegating tasks and finding strength in our differences during work time. This internship also enabled us with hands-on experiences to create specific procedures for accurate and efficient data collection. For this project specifically, our incremental trials of practicing varying aspects of our procedure, such as team roles, balloon cutdown, and data collection, taught us the vital lesson of performing each step methodically to ensure nothing is overlooked.
Subsequent to C's, I will continue making connections and nurture the connections I have made from this program.
I want to apply the skills I learned here at C's to become a mechanical engineer and develop assistive devices.
And to utilize the invaluable exposure I've gained to engineering experiences such as team problem solving and understanding complex hardware to bring back projects to my community.
Like we did throughout this internship, I hope to continuously foster collaboration across larger groups while also maximizing productivity, and to keep being creative through hands-on learning.
I plan on using the skills I learned from the C's program to develop projects that make an impact in my community.
I will take what I learned from the C's program to get involved in the maker community to build unique and impactful electronics and help inspire more youth and girls like me to pursue STEM.
In the future, when working with large teams, I'm going to prioritize being a good teammate and managing my time effectively.
Some things I have learned from this amazing C's internship is to ask all my questions, connect with professionals, stay curious, speak up for my ideas, and continue advocating for women in STEM.
What I took away from the C's internship is that I will continue to take advantage of as many opportunities as possible and practice my leadership, assertion, and networking skills.
After this internship opportunity, I hope to use the leadership, teamwork skills, and knowledge I've gained to better myself, my community, and empower girls in STEM.
These were the online resources we used.
Thank you for listening. Over and out.